Well, hello everybody. Thanks for stopping by here at the Lucene Revolution. My name is Kevin Waters, and we'll be talking about one of the contributions that I made to Solr and Lucene that I've been working on for multiple years, called the Solr Graph Query. And so kind of graph has been a topic since the 1700s, where Euler was contracted to figure out whether or not you could traverse the bridges of Kronensberg each one time in order to visit all of the sections of the city here. So it's really been a kind of a, we'll say it, a child of mathematics that people haven't really done a lot with, and I feel like now that we actually have a lot of data and people are starting to think about things in terms of knowledge graphs and things like that, it's getting to be a bit more popular, and we're seeing some good applications for it. First, a little bit about who I am. So Kevin Waters, I founded KMW Technology here, which is a Boston-based professional services firm, and we do search, big data, machine learning sort of projects for a lot of people. A lot of them focus around building like custom connectors and pipelines and kind of all the bread and butter sort of stuff, but we also get into a lot of very sophisticated like security filtering for documents and stuff, and we'll talk about how the graph query powers that in a little bit. So what is a graph? A graph is a set of nodes and edges. What is a node or a vertex, right? It is a data point that points to other data points, right? So we have a set of vertexes and edges, right? Sometimes called nodes and edges, nodes, vertices, things like that. So the idea is that you can actually model a graph by using a document, right? That a node is a document in the index, and that node, that document, has a field on it which points to other documents in the index. So there are a lot of different algorithms that actually allow you to traverse a graph, things like depth-first search or A*. What we implemented with the Solr Graph Query is a breadth-first search. So this is basically going to traverse a certain number of levels away, kind of in a lockstep sort of manner. And each one of these hops that we jump to include more documents, we refer to this as the frontier query. So basically what's happening is there's a recursive query operation that's going on here, which allows you to kind of traverse these nodes and edges by expanding that frontier out, like one hop at a time. So the graph query parser is built in. It's been in Solr 6. It uses the local parameters sort of query parser syntax in Solr. So you can see here are the various parameters that you can specify to actually do one of these graph traversals. The first thing and foremost is the query itself, which is an arbitrary any Lucene query that you want to put at it, and that defines your what I call the root nodes, or the starting point for your graph traversal. So you identify a universe of documents that you're interested in, and you specify which field represents the field that as the node ID, and what field has the either single or multi-values that point to other documents in the index. That's the from and the to. You can also specify how deep you want to go with your traversal. By default, it's going to traverse everything. So -1 will continue traversing until there is no more document to explore. All the edges have been exhausted. There is, you can also, because there's some nice little optimizations, you can specify whether or not you want the documents that matched your original query to be included in part of the result set or not. And then we also have this concept of a leaf node. And in a graph, any node that does not point to something else we refer to as a leaf. So you can also specify whether or not you only return the leaf nodes for that graph traversal. So these are just kind of some nice and easy things, because those filter cache entries, those bit sets existed. So it was just kind of a very lightweight feature to throw in there that actually gives you a lot of power and flexibility in how you actually filter and return your documents. So from the perspective of a query, somebody said to me once that a graph is a filter on top of your data. So when you look at Solr, we're really talking about filter caches here. And yes, indeed, that actually is basically giving you a subset of your data that you're looking at. Some of the key design features that we had here is that it has to traverse everything. We don't want to leave any edge behind. So this is a complete traversal. This isn't like, oh, we're going to only pick the top, interesting concepts. No, this is complete traversal. We wanted to make sure that this was very efficient in terms of how it uses its memory. One of the other key things here with graph traversal is you can get into what's called a cycle, where one node can point to another node, that node points to another node, ultimately it creates a circle. One of the beautiful things is because we use a bit set for the filter cache entry, we actually know the history of where we've been previously. So from that perspective, this approach actually gives us cycle detection for quote unquote free. No additional memory is required to do cycle detection. Of course, a document can point to either one, or a node could point to one other node, or it could point to a list of nodes. So we wanted to make sure that multi-value fields could be supported on either the node ID or the edge ID. Just keep it as flexible as possible. And there are some other concepts too, where you might actually only want to traverse into another node if it has a particular characteristic, traverse only into another type. So with each hop of the graph traversal, we have a traversal filter, which allows you to pass in another arbitrary Lucene query, which will restrict your traversal. And because this is actually all done down at the Lucene level, this works seamlessly with any faceting or any of the other features that you might want to use from Solr. So you can do graph traversal, identify a result set, and then do analytics based on that graph by using faceting, JSON facet API, whatever you want to do. So I touched on the key issue here, which is keeping memory usage as low as possible. So what I basically say is one bit set to rule them all. So if you think about it in terms of the way that the fixed bit set works, in Lucene you have effectively a bit set that's the size of your index. But with 100 million documents in the index, we're only talking about 12 megabytes of RAM for that bit set. It's basically the same size as one filter cache entry. There are two other bit sets that are involved with the graph traversal. One bit set is the initial documents that match your original query. Those are your root nodes. And another bit set, which is any document in the index that does not point to another document, has no edges. And so the leaf node bit set allows us to skip doing the doc value lookup for the edges during the hit collection. So there are a couple things when you set up your schema that you probably want to do. Doc values, of course, the community knows it, loves it now. They are so much faster. You don't need them turned on, but they're much faster. And you'll see actually your graph traversal will probably be 3 to 4 times faster if you enable doc values. It is unlikely that you want to tokenize your node and edge IDs. So unless you really want to do it that way, you probably don't want to tokenize those. So leave them as strings, untokenized, and turn on your doc values. The depth, if you know that you're only going to take maybe 4 hops away, if you specify the max depth of being 4 hops, then there's an optimization that it doesn't even bother with the edge lookup at the end. So if you can limit your depth, you can also have a much better performance in some cases where that's applicable. So one of the key use cases for doing this is actually because I feel like the way that search industry has been doing document security has been completely wrong, right? One of the worst things that you could possibly do is take all the ACLs and put them onto a document, and then all of a sudden you see that like somebody is added to a group or removed from a group, or a set of documents are moved into a new folder, and all of a sudden you have to re-index all your data. And it takes a very long time potentially for that to propagate through the index, leaving you in a very insecure state for a period of time. So I think the mantra is never re-index your data. If you have a user being added to a group, index one document, which represents that change. Don't re-index the rest of your data. That's too painful. And the graph query actually allows for this to happen. So here we'll talk about an actual example. Let's say we have, for example, 2 users. that are members of groups, for example. So in terms of the traversal, we have the Boston sales rep who's a member of the Boston group, which maybe has access to this particular document here, and then you got the New England sales group has access to that document. And you can see that there's a member of sort of thing. So we have a group of a group, potentially of another group. So being able to do the query, your initial query, starting at your user record, traversing to your group records, and ultimately taking the last hop of the graph to the actual documents that you're going to return. All right. So if you think about the documents in your index, here's kind of a fictitious little index that shows the basic traversal where we have user records, we have group records, and you ultimately have documents, right? And if we look at the path of the traversal here, you can see that user 1, this is my root query that I'm going to start the graph traversal from. I go from the user record to the group record to the other group record, and ultimately to the documents themselves. One of the key things to point out is that these document records do not have pointers to other records. These are referred to as edge node or leaf nodes. So that parameter, leaf node only, allows you to only return these documents and very efficiently exclude all of your access control records. You can see just another example here where that user actually is a member of this group, so it kind of just traverses directly that way. The amazing thing is actually what used to be a very difficult thing where at query time you'd actually have to go, you'd have to resolve all the permissions associated with the user, you'd have to put that in as a big Boolean OR query, for example, can be replaced with a single graph statement that says traverse from the node ID to the edge IDs, return only leaf nodes starting at user 1. And if you take this and you pass it in as a filter query parameter, you get the added benefit that this is going to be cached the next time the user comes in. So it's very efficient in terms of doing this security filtering. You might pay a little bit of a price to do the original query to generate that filter cache entry up front, but it's going to be cached for you for subsequent queries. So as far as an end user is concerned, the performance of any of their searches is going to be the same effectively as if there was no security filtering at all. It becomes just transparent in terms of performance. So there are some limitations. The current graph query is limited to a single core. But in many cases, if you're smart about how you index and route your documents, you can still get a distributed index, right? So you can distribute your documents, but just make sure that your user and group records actually exist in every single shard, right? So you might have a baseline of about 50,000 records for all your permissions across all of your shards, but you can still distribute the documents that you're searching across all of them. So security filtering is definitely one of the key advantages of using it and one of the best use cases, but it's not limited to that. Let's say, for example, you actually want to do a recommendation engine, right? You can actually model an end user's behavior on a website. You have users, you have actions that they've taken, and you have items, right, that they've maybe bought or sold or whatever. So you can model this user behavior and their actions and the items, of course, as a graph, right? And you can use the graph traversal, say, for a given user, let me find other users who also purchase this sort of thing. Based on those users, now I can traverse into the items that they also purchased. And maybe I don't want to return the original identifying records, so I return root equals false. So you can see, basically, if you have an item record, you have the first hop gets you to their action records. The next hop gets you to a user record, users that bought something. The next hop gets you back to an action, ultimately to an item. So what you can do is you can say, hey, every time I have this graph, I can take 4 hops and get from one item to a related item. So there's a 4-level hop, and then you can just kind of do your query and say, effectively, people who bought this also bought that. Again, with one very discrete, simple graph query statement to do that traversal and identify those records for you. So recommendation engines, that's fun. But there's also some more interesting things that you can do, right? When you think about, there's an open project called WordNet by Princeton University. Basically what they have is a hierarchical modeling of all the words in the English language. And they have these concepts of a hypernym and a hyponym, basically saying that a jaguar, for example, is a type of a cat, right? So in that case there, a jaguar is a hyponym, or it's a more specific type of cat. So you can say, a cat is a type of animal. And you have this like sort of hierarchical model. Well, it seems like that kind of fits very well. So you can actually say, if you want to know all the things that, are a type of jaguar, you can traverse up the whole WordNet hierarchy here, and you say, give me, starting with jaguar, traverse up is a type of cat, is a type of feline, carnivore, blah, 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 all the way up to the top. And so you can actually do this graph traversal. You can run this search, it's very efficient. It brings back all the data that you need in order to render all the connections between these things. Interestingly, you can actually intersect these graph traversals, right? So maybe you're actually interested in what are all the paths in this network that get me from one thing to another. So I can actually flip the direction of the traversal by changing the to and the from field. I do one query for jaguar, one query for animal, and basically by the intersection of these two graph traversals, we can actually use inductive reasoning, right? Basically, we can use this graph query to provide like generalized artificial intelligence and answer a question, for example, is a jaguar an animal, right? And if there is an intersection between these two things, and if this is a non-null result set, you can answer that question and say, yes, it is, right? Wikipedia is an interesting data set, right? You have pages, and these pages are very highly linked to other pages and stuff, and there's a lot of reference. One document will point to maybe 50 or 100 other sort of documents. Wikipedia pages also have like the info box section, and the info box section might have something like, this is a page about a person, this is a page about a book, this is a page about an author, a scientist, whatever. And it's kind of nice, but the tagging of these info boxes are actually more specific than what the user is searching for, right? So if I'm searching for, show me all the pages that are about people, I would have to actually know, is a scientist a person? Is an author a person, right? So what we did, we can start and we say, well, WordNet actually knows that a scientist is a person. I can do my graph traversal, starting with person, find me all the things that are a type of person, right? And I can take that result set, I can do a search against Wikipedia for, this one here is an example of searching for the page on graph theory and taking one graph traversal hop out to the side. And it's kind of tough to see here, but the facet counts here is you have scientists, you have algorithms, you have the journal, publisher, organization and stuff. Maybe I'm interested in who are the people that are highly related to this concept of graph theory. So if I intersect the query for the WordNet traversal, I can actually resolve all the things that are scientists, all the things that are people. I can intersect that with the pages that were related to graph theory and actually come up with a result set which is just about the Wikipedia pages for people, and in addition to that, you have all the linkages between these things. So, you see William Ronan Hamilton here, for example, is like the father of graph theory. You kind of see who are the important people related to this particular topic and concept. As I kind of hinted at, so this is a fully nestable sort of query, right? So you can actually take one graph query, you can nest it inside of another one. Maybe you want to actually change which fields you're traversing, right? So by nesting graph queries, you can actually start traversing one set of fields, nest it inside another one, and change the fields that you're going to be traversing. All right, so here's the example where the original query was all pages related to graph theory intersected with those things that are a person from WordNet, and then ultimately joining on another field here, which is the entity type, to actually do the restriction. So I'm using the WordNet database to refine my query, if you will, to restrict it. And basically, it's kind of like doing this ontological sort of search, or almost like a semantic search. I searched for person, and I found a scientist, right? There are, so people that, I do have to give a shout out to this. So the streaming aggregation does provide another method of graph traversal, which is the gather nodes stuff that was contributed by Joel and stuff. So for those people that actually really want to do some sort of like brute force sort of approach, there are options to do that as well. I feel like as time has been going on, this has been getting a lot more sort of attention, and there's multiple implementations now. You see Elastic has their graph search, now there's this graph search. So there's a lot of interest, I think, in the community for this stuff. we do have a version of the graph traversal that does work in a truly distributed manner, but in order to do that, we actually needed to introduce Kafka to be the frontier broker, so that every time you do the graph traversal from each node, there's a shuffle component where each node has to publish its portion of the frontier, and the other shards listen to that. So it's kind of like a pub-sub model, and we use Kafka to actually coordinate that and make sure that all the graph traversal across all shards happens in lockstep with each other. So if you want to know about that, if you actually think you have a distributed graph problem, come talk to me, and we'll talk to you about that. Some of the questions: what sort of things should we be looking at next as a community to bring to Graph Query? Right now, the current Graph Query does not have any sort of concept of relevancy or scoring. That was done on purpose because it's really for high performance, low memory footprint. But potentially we could do include some things like how many edges point into a particular document, do like link cardinality sort of calculations. Keeping around like what's the minimum path or something like that, do driving directions. The way it is right now, like visualization libraries like D3.js are you have to do a little bit of work to get the result sets to visualize properly, so maybe we can improve that there, and of course the distributed work, which I would like to replace Kafka with something more native in Solr to do that. So these are the tickets that were kind of related to the Graph Query. The original one there is 7543 was the original ticket. There was a performance optimization that went in. I think that was 8632, and then actually I posted the patch for the distributed traversal, just more or less as an example for people to look at on the last ticket there. So I kind of talked through that a little bit fast, but so maybe I'll kind of. Now these are extra slides. Okay, so maybe I'll just open it up to the crowd if you guys have any questions about this. Everybody's tired after a couple days of conferencing? Yeah. Right, so for the cases where you're actually solving, the question was how does performance compare to Neo4j? So the function or the performance characteristics of this graph query is really a function of the number of unique edges that you traverse. And so the bounding factor is really like the performance of doc values returning this. Generally speaking, what I've seen on my laptop on relatively large result sets, it traverses something about 250,000 edges per second. So in terms of Neo4j, I would say it's as fast, and for particular use cases, it might be considerably faster. Right. Yeah, so semantically, a one-hop graph traversal does a join for you, right? So I see the graph traversal as a more sort of generic operation than just the join. If you do want to, you can actually use the join query to go across cores, which is one of the things that's supported there. So you could do a graph traversal on one core and then use the join query to get you into another core if you wanted to do something like that. 6 of one, half a dozen of the other. It really is pretty much. The trace stuff, right? That was Career Builder with, is that which talking? Yeah, that's not using this, but I think that probably you could identify the data sets that you would want to bring into those learning algorithms maybe more easily by doing this traversal. So it's a slightly different thing. So, Jeff? Yeah, all of this can do that. The reality is you're basically identifying all of the nodes in a network that will get you two endpoints. And I probably glossed over it a little bit there, but the example with WordNet, where I was answering the question of is a jaguar an animal, that's actually two graphs intersecting with each other, and the result set that's returned is actually effectively every path that connects those two endpoints. So if you want to do this sort of hop analysis and figure out how is person X connected to person Y, did somebody from group A talk to somebody in group B about topic X, these are just multiple graph traversals to identify, like, did these people communicate with each other? And if they did, what were they talking about? Yep, exactly. Exactly.
Is there an overhead for the depth, or is it really more tied to edge traversal?
It's really tied to edge traversal, right? So the number of unique edges that you traverse is the binding factor in terms of the performance of this. There is an optimization if you say, I'm only going to go one hop away. Once it knows that it's done that one hop, it's not going to bother with the doc value lookup. So if you know that you have a fixed depth that you're always going to go, you get a slight performance of actually specifying the depth. Yeah. But I've done, like, simulated, social networks of like 100 million documents on a single box, and, we'll run the query. It might do 1900, hops in that graph, and it still returns in a relatively, like close to sub-second. Yeah.
I know there's a Jira out there, maybe more organizations, but just quickly touch on Gremlin and Superpop thoughts.
Right. So one of the things that I didn't attempt to address here was the query language, right? So so we have the query syntax. I wanted to make it feel as similar and familiar to Solr syntax for better or worse. When it comes to other languages for graph traversal, I mean, Neo4j has its query language, and I think that you could probably implement a lot of those interfaces and just power it in the back end with this. So that layer of translation between something like Sparkle or Gremlin, whatever, that's kind of left up to the community to do, I guess. Yeah, contrib's welcome, always, always.
You mentioned that we could sort of co-locate the user and group records with the rest of your documents.
That's right.
If you wanted to do like
If you need to do distributed, like high data volume security filtering, yeah, you broadcast the user and group records to every shard.
instead of that, what about potentially keeping the user and group records in a separate collection or separate core that's just a single shard maybe?
Yeah, so that's another possibility too, and so you could do the graph traversal on that separate core and then wrap that into a join query to get you into your documents. Yeah. I've thought about it. The framework is now there. Like, the code base is set up. We have the graph terms, hit collector and stuff that kind of does a lot of this stuff. So I think it'd be relatively easy to extend it. But one of the issues there, of course, is that in order to discover that, the amount of memory that you might need during the traversal could be very large. So that's one of the things that I've always been very, very sensitive not to introduce, that sort of functionality.
So why is doc value so much faster?
Well, all right, so between using like the field cache versus doc values is just a much more efficient data structure to actually say, when I'm actually in the index and I have the index reader, right, it's going to be much faster to, rather than having to uninvert the field and actually resolve what those field values are, doc values is just a much faster way to do that. So when this traversal is going on, one of the biggest things that it does at every hop is during the hit collection, it has to iterate all the documents that match that query, and it has to look up the edge IDs. And effectively, it's going to gather those edge IDs together to create like a gigantic OR query, effectively, that takes the next hop. So it's really looking up what are all the unique edge IDs that you want, and doc values is just a much more efficient way to do that rather than using the uninverted reader. What was the... Yeah, well, I think at the end of the day, it is like a shuffle problem, right? Where each node is accumulating its portion of the frontier query, and it has to shuffle that to the rest of the nodes, right? So it's really just, it's really more of an object broker problem. And when you think about like map reduce, there, people don't say, oh, it's partition map, partition reduce, shuffle, all that stuff. But it's that shuffle part. And the key piece to make that happen is actually some sort of an object broker, a very low latency, high scalable object broker, which is why I chose Kafka to do that. Yeah. So you're talking about like cycle detection and stuff. So like. Yeah. Exactly. So what you want to do, so it's kind of like searching arbitrarily complicated or arbitrarily nested like JSON documents, for example. And if you decompose your JSON document, each one is a separate document in the index, and they have a pointer to the parent record, right? You can use the graph traversal to actually do proper traversal and search on that and maintain like the actual constraints. So I don't know if that answers your question. I'm sorry. Mm-hmm. One traversal to rule them all. Okay, we got 5 minutes. So, yes? So, when you think about it, right, it's your data, right? And I kind of touched on that a little bit with like WordNet. There is some sort of semantic information there. I search for a person and I want to resolve all the things that are a type of person, right? So in one way that kind of provides you a very high scale sort of synonym expansion, if you will, that you can use to actually infer what is the user actually searching for. For the Wikipedia example, I searched for a person, but actually what my drill down was on scientist and author and stuff. So from that perspective, you can do those sorts of semantic types of queries like this. Yeah, no big deal, but you can do it all in one query. You just add them as multiple filter query parameters. So I'm only executing one query, but yeah, there's multiple graphs there. Yeah, absolutely. Yes? So gather nodes and streaming expressions is built on top of the export handler, right? So that's going to do brute force, export all of your data, and then the streaming aggregation framework is going to filter down those topic streams, or those tuple streams, right? So it's kind of more of a brute force sort of thing, whereas this is implemented down at the hit collector level in Lucene, and all I'm ever doing is banging on one bit set. So from my perspective, it's the most optimized approach to it, whereas maybe the gather nodes is a more generalized approach. So this has sort of semantics associated with what you can do there, whereas gather nodes might be a more general purpose framework, shall we say.
Is there value in having two completely different ways of doing the same thing, but different people?
I think variety is the spice of life, right? So that's a good thing. And I work with or chat with Joel a lot about these sorts of concepts and stuff, and we by having other people in the community, other sort of approaches, it kind of improves it for everybody, I think. Yeah. Yeah.
Have you done any experimenting with documents as edges so that you can have complex edges?
Yeah, so one typical use case for that is a lot of times you might have a metadata record and then you have an attachment, or like an email and an attachment or something like that. And you might want to search the attachments but return the metadata record or return the email. So you can actually do your query against the attachments and take a one-hop traversal to the metadata record and return the metadata record. So kind of doing that like, we'll call it like nested sort of queries or nested document sort of support. Yeah, you can do that. Yeah, and that's actually a pretty common use case. So, especially when you're talking about like attachments, right? So you have a document or a page that's got attachments on it. You want to search the attachments, so you want to return the original page.
I think the question might be, though, if you need to alternate back and forth between different types of entities, like you have one type of thing, I guess it'd be like if the attachments contain things that you were searching for, but then that pointed into other metadata that you needed to turn back into more attachments, and like kind of alternating back and forth.
Yeah. So actually I probably should have put this on future thoughts too, is the traversal filter allows you to kind of restrict what you're going to traverse into. So you can say, I'm going to do a graph traversal, I'm going to add traversal filter that says only traverse into things that are of type document, right? Or I only traverse into things that are of type email, for example. And it'd be nice to maybe change the syntax so you could actually pass in an array of traversal filters, and it could actually cycle through the array at each hop. So you could actually say first go into emails, then go into user records, then go back into emails and stuff like that. And that would be a really nice improvement. We've thought about that quite a bit actually. And it wouldn't be that difficult to add. I just don't know how that would work in the syntax. I think the syntax would start getting a little hairier than it already is, shall we say? Yeah, Jeff. Yeah. Sure, sure. And you might actually want to do a traversal and then put a facet on your edges to figure out what did I actually traverse. So there's a lot of like data discovery sort of things that you could do with this as well. Yeah. So I think that's just about it. I say thank you very much for your time, and enjoy the rest of the conference.